Hello, my name is Daniel Cremers. This talk is about leveraging the power of deep neural networks for camera-based 3D reconstruction. The work that I'm presenting has been done by current and former members of my team, in particular Zora-Lena, Nan Yang, Lukas von Stumberg, Rui Wang, and Jacob Engel. We've witnessed the breakthrough of deep neural networks over the last decades, and this is one of the most known achievements is their success on the ImageNet challenge, where they outperform even human-level performance at this point. And the success has been quite impressive, and it's been carried over to many areas of computer vision. For example, beyond doing object recognition, we can also do a low-level image analysis, for example, estimating optical flow. This is, for example, a work called FlowNet, where we basically just take two input images and train a neural network to generate the optical flow between them. In addition, we've seen great achievements on other low-level challenges, for example, semantic image segmentation, where we train neural networks to segment images. This is one example by Alex Kendall and collaborators. This is a work on deep networks for single object segmentation in videos, and as you can see, we can get very precise segmentations from neural networks. And so neural networks have achieved great successes in computer vision and beyond. Yet I would say one of the holy grails of classical optimization-based techniques is the reconstruction of our 3D world from cameras. I don't want to go too much into why that is, but possibly it is because the space of conceivable reconstructions and conceivable input data is very large. And as a result, it is not easy to get sufficient training data to cover all conceivable cases. In this talk, I will highlight three developments. Firstly, I will talk about deep neural networks for 4D scanning, so spatio-temporal scanning. And then I will talk about deep learning for the problem of visual SLAM. I will first introduce techniques of direct visual SLAM and then show how these can be boosted by the power of deep learning. Camera-based reconstruction is a challenging and fascinating area. This is a result from 2014 that shows that we can nowadays recover from synchronized videos the 3D structure of objects at fairly high level of detail, where the entire rope of this rope jumping girl is recovered from the videos. We can also leverage other types of sensors, for example, RGBD sensors. Here's an example of a technique that allows to scan humans. Here, for example, you see it scans a person in real time, basically concatenating these RGBD scans into a coherent 3D reconstruction. A colored reconstruction that can be immediately uploaded to a 3D printer so as to generate copies of the world around us. And as you can see, this has become quite popular in our lab. People like to get their own scan. It's like tangible memories that you can create for friends and family, or as avatars in a game if you want. It's become so popular here, for example, the former president of TU Munich asked himself to get a scan, and so he created a virtual copy of him here. This is a standalone scanner where on the push of a button, the robot arm moves around and creates this kind of colored model of the person, and he was quite happy with the result. In the meantime, we have already scanned our Prime Minister, and so it's become quite successful. Nevertheless, you can carry this scanning further to 4D, where you scan not just one object, but an action in space and time. And one of the challenges that Zora-Lena addressed is how to deploy deep neural networks to improve the quality of 4D scanning and 4D animation. It starts with a 4D capture. Then we create a subspace model, a linear subspace model, and then what we do is we use a conditional GAN in order to generate high-resolution normal maps. This is quite powerful, and it allows you to generate very high-resolution details on the low-resolution subspace model. So you boost the precision, and you can basically train neural networks with training data to create high-resolution geometry from low-resolution input, using this subspace representation of the shape, and then on top of it a normal map. We use a generator in the form of a unit that allows coarse-to-fine processing of these details, and here's results that show that this works fairly well for physics-based simulation. This is a default simulation with commercial software, and as you can see there are wrinkles, but they look less organic, they are less detailed, and often also not necessarily very consistent. So it looks okay, but it's not sufficiently detailed, and so you can typically see that it is a simulation. Here instead, the reconstruction using the so-called deep wrinkles approach with a generated normal map, and as you can see we have far more fine-scale details that are observable in these reconstructions, so it looks significantly more realistic. This is one way to leverage deep learning based on a normal map representation of details to create further details, and here's more examples of this technique. This is the approach pix to pix, and there is no temporal consistency. Instead, here is the deep wrinkles. They actually integrate also some form of temporal consistency of the details over time so that you don't get any oscillation phenomena. Here's an application to virtual humans. This is the approach with deep wrinkles. This is in fact Tony acting in front of the camera here, our co-author Tony Tan. And here you have Zora, the first author of the paper, and here you see the simulations. This is without deep wrinkles. You see there's very little details, but once you add the wrinkles you get far more details. So we can boost 3D reconstruction from cameras with deep networks, but in addition we can raise the question, can we also do 3D reconstruction from moving cameras, where we need to solve the classical problem of visual slam. Visual slam is a long-standing problem, traditionally known under the name of structure from motion. Erwin Kruppa, one of the pioneers, an Austrian mathematician, back more than 100 years ago already proved a very seminal result. Namely, he showed that if you observe 5 corresponding points in 2 views, you can recover the camera motion between the 2 views and the 3D location of these points. This was quite a breakthrough, and it basically paved the foundations for modern computer vision, 3D computer vision. In fact, this led to what I call the classical pipeline of camera-based 3D reconstruction, where we follow closely in Kruppa's footsteps. We take 2 images, we extract points, and in order to have corresponding point pairs, we identify correspondences based on descriptors such as SIFT, SURF, BRIEF, or more modern deep learning-based descriptors. And once we have a set of corresponding points, we can then recover camera motion and 3D structure using techniques like bundle adjustment. This pipeline works quite well. It is very impressive, but nevertheless it is suboptimal in various ways. Most importantly, we only take 2 images rather than a whole sequence of images, and moreover we extract these points, and this point extraction is heuristic, so invariably in any errors you make in associating correspondences, these errors will propagate into your subsequent reconstruction. And in order to recover from such errors, we have to add components like ransack, where we resample potential correspondences and recompute models until we get a consistent model. This is rather tedious, it is rather heuristic, and so it raises the question whether there is not a more direct, more optimal way. And this leads to what is nowadays often called direct methods for visual SLAM, where we aim to reconstruct the world and the camera motion directly from the sensory data, from the intensities or color values of our camera. Why do we promote this technique? Well, it's obvious. Anyone who works in sensory analysis can confirm the more closely you work on the raw sensory data, the more likely you will get optimal solutions, and this should propagate into more precision and more robustness. One of the first direct SLAM methods, definitely to my knowledge, the first large-scale capable direct SLAM method, is a technique that we called LSD SLAM, for large-scale direct SLAM. This approach was developed by Jacob Engel. My main contribution was to coin the name LSD SLAM, which I believe helped a bit to more popularity. The approach is rather sophisticated. This is an overview slide. It starts on the top left here with the input video streaming in, and then there's two alternating threads, one that does tracking of the camera motion and one that does depth estimation for selected keyframes, and then these depth maps for the keyframes are merged into a global reference world reconstruction. What makes it large-scale capable on the top right is a pose graph optimization that we adopted from LiDAR-based SLAM. The idea being that you compute in a second thread a consistent estimate of the full trajectory, consistent in the sense that it is consistent with the pairwise alignments of keyframes that we computed in the tracking approach. This tracking approach, the whole method, is direct in the sense that, for example, let's look at this tracking component here. We track the camera motion, the 6 parameters Xi modeling rotation and translation between consecutive frames, between, say, the current frame I and some keyframe IKF, by aligning these images. So find a rigid body motion GXI such that the two images perfectly match in terms of the brightness values. And so, as you can see, this is really the key difference of direct methods, is that everything is driven by brightness consistency. And in fact, we will look more deeply into this in the remainder of the talk, how we can further boost precision on this level. Since we only estimate 6 parameters in a coarse-to-fine manner, this can be easily done on a single thread, a single core of a CPU, even a laptop CPU, in real time. And so we can use the multiple cores of a laptop CPU to run the camera tracking and the depth map estimation and the pose graph optimization. All of it is integrated here. Top left you see the camera, in the center the laptop, and on the right the reconstructions of the camera motion and the 3D point cloud. Everything is generated, as you saw, in real time on the fly. And as you can see, we can recover fairly large environments, not only a desktop environment, but whole outdoor scenes with tables, chairs, etc., from just one single moving camera. As you see, there is qualitatively fairly little distortion here in these reconstructions, and indeed our ambition is to minimize the distortion, to minimize the overall drift. The reconstructions recovered by LSD SLAM are not dense, but what Jacob calls semi-dense. So for roughly 50% of pixels, we get a depth value associated to them. If you look into LSD SLAM, you note that camera tracking and 3D reconstruction are done in two separate threads of the optimization method. As we know from Krupa's work, the reconstruction of camera motion and 3D location is actually a coupled problem. And hence, not surprisingly, in the follow-up work, direct sparse odometry, Jacob proposed to estimate things jointly. Here you see the system in action. Top left is the input. Note that there's even people walking through the scene. The algorithm is extremely robust to moving objects. On the bottom right, you see the reconstruction of the camera trajectory and the 3D world at very high level of precision. It allows us to go through an entire subway station and back around the other side. And we obviously make errors across the way tracking this camera over so many frames. Here you see the so-called drift that we accumulate. The bicycle on the top left is reconstructed twice here. I would say the drift is maybe 2 or 3 meters on a distance of hundreds of meters, indicating that the total drift is in the range of maybe 1% or less. In fact, this leads to the question of how can we quantify the performance of this method, a question that is becoming increasingly important in all areas of computer vision, especially in the deep learning age. There are many ways to quantify performance. One way would be to simulate the data, simulate 3D worlds, simulate videos. Then you can quantify the performance very easily, yet you get the performance in that simulated world. And I think we all agree that the world we live in is not a simulation. So instead, Jacob proposed a way to directly assess the performance in the real world. He recorded a lot of diverse videos with different lenses, more fisheye, more perspective lenses, in different environments, some indoor, some outdoor, some faster motion, faster rotation, some more textured, some less textured. Very diverse sequences. They all have one thing in common. They all loop back to where they started from. Which means that for each of these sequences, we don't know where the camera was halfway through the sequence, but we do know where it should be at the very end. And this allows us to quantify the total drift per sequence. And so the idea is if we have enough such sequences, this gives us a statistically reliable estimate of the performance of a method. And so we can plot this performance for the translational drift, the rotational drift, and the scale drift, shown here. On the x-axis is the error that we achieve for a given sequence. On the y-axis, the number of sequences where we achieve that error. And so clearly you want to be in the top left here. We compare to what we consider the state of the art in real-time visual SLAM, a keypoint-based technique, very powerful technique called orb SLAM from a team in Zaragoza. The dashed line is always the real-time performing method. Solid is if you have a bit more compute. These plots can be read in many ways. For example, we can say what is the maximum error on the best 300 sequences. While orb SLAM has an error of around 6, ours has an error of around 1. So you could argue the error is reduced by a factor of 6. Similarly, if you want to impose a maximum error of 2, how many out of 500 sequences can you track with that error? While orb SLAM can track 100, we can track 400 out of 500. So we also get a significant boost in robustness. Because obviously you don't only want precision for a method, but you want this method to work in as many cases as possible. Why do we see that significant boost? We believe it is because it is a direct method, because we leverage all conceivable information from the input video and not just a subset of heuristically pre-selected points. We built up on these technologies in a startup called Artisans that we created around 2018. This is a picture of a recent team event. The company Artisans develops sensory systems that include cameras, inertial sensor, and GPS, all integrated, calibrated, and time synchronized. In addition, we develop spatial AI algorithms that build up on techniques like DSO and further improve them to achieve maximum performance in terms of precision and robustness and scalability. Here is one result achieved at Artisense, an extension of direct sparse odometry to stereo cameras, stereo DSO. And as you can see, we can use this technique to recover very large environments in real time with very little drift. As you can see, we can drive around a block and things almost perfectly align here. So this is one way to further boost the performance and to also get the scale of the world, is to use a second camera. It increases the robustness, it reduces the drift, and it provides you the scale because you have the baseline. And so there's tons of such videos run on different data sets, our own data set, but also on Kitty and on other cityscapes, etc. Here's more examples. I think in the interest of time, I will cut this short, but I refer you to YouTube to watch many of these videos, fly-throughs through the world that we recovered with just 2 onboard cameras. You can use the power of deep neural networks to semantically label these point clouds, also an achievement that we attained at Artisense. We deployed our sensory systems in a fleet of cars in Berlin and drove around 8,000 kilometers of distance and mapped the whole town, or large portions of the town. We can distinguish 20 classes of objects where we label not the images but the 3D world, the drivable area in red, cars in blue, sidewalks, buildings, vegetation. And here you see some glimpses as to the environment that we were able to map with the fleet of cars in a matter of just a few days, essentially, with very low-cost hardware, so we don't need lidars for this. Cameras are sufficient, and that dramatically reduces the cost of these sensory systems. The question, however, that I want to address here now is how can we leverage the predictive power of deep learning to boost the performance of visual SLAM, to get more precision and more robustness, less drift, more accuracy. There has been a lot of efforts in this direction. And as I said, deep learning has had great successes in all areas of computer vision, but I would say to date, the reconstruction of the world from moving cameras is a hard nut to crack with deep neural networks. And while these approaches are quite powerful and have shown nicely that you can train neural networks to create camera motion and 3D structure, most of these approaches do not exhibit state-of-the-art performance, in the sense that often classical optimization methods provide more accurate trajectories, more accurate odometry, etc. I believe this is partially due to the fact that these approaches are often formalized in an end-to-end learning fashion, where ideally you have a big deep network, in go the input images, outcomes, trajectories, and 3D reconstruction. And so what we are promoting here is to maybe advance hybrid methods where we integrate deep neural networks into a classical SLAM approach. The first such result is a technique that we called DVSO, Deep Virtual Stereo Odometry, by Nan Yang and collaborators. It starts with deep networks that can predict from just one single image the depths of the scene. And this is quite impressive, but in some sense not surprising. Even for humans, if I were to show you such an image, you could give me an estimate of how far the different things are in the image. Why? Because you know the world that you're looking at. And this is interesting to observe. For years, I've told my students that we cannot recover the scale of the world from just one moving camera. It turns out this is not true. You can recover also the scale if you know the world you're looking at, if you know what size these objects typically have, the cars, the signs, etc. One such network was promoted by Kuznetsov and collaborators, CVPR 2017. Nan Yang and collaborators built up on this network and further boosted it to what we call StackNet. And as you can see, we get significantly sharper predictions of the depths from one single image. We can now use this depth prediction and run it on each keyframe of our sequence. And then we can impose this depth map prediction of the deep network into the classical SLAM method. We do that on two levels. Firstly, we initialize the depth maps for each keyframe with the prediction of the deep net. And secondly, we add a term in the loss function of the classical SLAM approach that assures consistency with the prediction of the deep network. And what we get is called deep virtual stereodometry. It's a technique that uses a second camera to train. So it's in that sense self-supervised. It doesn't need ground truth for supervision. All it needs is two cameras to train and one camera to run. And so from a single camera, you can see we can get very, very nice reconstructions with almost no drift and very high precision. And these are indeed metric reconstructions. And we can compare to other methods. Here's a comparison to some of the state-of-the-art methods in stereo-based SLAM, stereo LSD SLAM, stereo ORP SLAM, stereo DSO. And now comes this method, DVSO, which you can see performs on par, if not better than these methods. The black numbers are the best performing, cursive are the second best. And note that this method can rival with these stereo methods, although it only uses one single camera. So you can say basically we use the power of deep networks to replace the second sensor. In some sense, and this is what we call the deep virtual stereodometry, the deep network hallucinates the contribution of the second camera. And we will see that we can take that idea even further. In fact, this is a method called D3VO, published at CVPR 2020. The idea is that we use deep learning now on multiple levels of the SLAM pipeline. Firstly, we can use a deep network to predict the depths. Secondly, given two consecutive frames, we can train a deep network to also predict the relative camera motion between the two frames, deep pose. And lastly, we can use deep networks to also predict some notion of uncertainty. And all of these predictions can then be integrated again into the classical SLAM pipeline, both in the front-end tracking and in the back-end optimization. As we saw, we can train deep networks to predict the depths. Given two consecutive frames, as I said, we can also predict the relative motion of the camera, rotation and translation of the camera. And this allows us then to align these two images. And so we can train this approach in a self-supervised learning manner, where we have a residual that basically measures brightness consistency for all pixels. And this is the loss function that we can use to train the neural network, the pose net and the depth net. Once we do that, though, we find that due to aperture problems, aperture changes, typically the brightnesses are not preserved. And you can see, as you see here, the two images have significantly different brightness patterns. Turns out we can also use PoseNet to predict these aperture changes, or to basically predict a color transformation between these two images. We use an affine model here with two parameters A and B to align the two images, as you can see on the right. So we have the source image I, and we have that we align with respect to the target image I prime. Now this compensates for aperture changes and allows to nicely train the neural network in a self-supervised manner. Yet, as we all know, the world we live in is not always Lambertian. So if you have images like this one, you will have areas, for example, the windows, metallic structures, and other locations where brightness consistency cannot be assured from one frame to the other. It turns out we can train a neural network to estimate what is often called aleatoric uncertainty. For example, there are papers by Alex Kendall and collaborators and by Maria Claude and collaborators who also use this concept of estimating uncertainty. And so we can train our neural network now with a modified self-supervised loss, where we basically modulate this brightness consistency with the uncertainty. We basically reduce the contribution in areas of high uncertainty. And then we can train this total network to also predict this uncertainty. Here you see a result of the uncertainty prediction, and indeed in the window areas, on the cars, on metallic structures, but also, for example, in the trees, where you often have motion and brightness is not preserved from frame to frame, the uncertainty is estimated to be high. And so this works fairly nicely, and we can now integrate all these predictions of this neural network into the SLAM approach. As I said, we do this on two levels. In the front-end tracking, we basically impose this in form of a nonlinear factor graph for direct image alignment. And the back-end optimization, we add respective loss functions to the overall cost of the SLAM approach that impose consistency with the predicted quantities. I don't want to go too much into detail here how this is done, but you can read it up in the paper. Let's look at some evaluation here. We'll start with monocular depth estimation, and when we compare to one of the state-of-the-art methods, namely MonoDeps2 on two datasets, the Kitty and the UROC dataset. And as you can see in this ablation study, we actually outperformed the state-of-the-art by quite a bit. Again, black is the best performing, and here in blue, second best. Now, deep networks often have a shortcoming when you try to apply the trained network in a different environment. Very often the performance drops quite significantly. So what we did, basically as a test here, we evaluated it also on cityscapes. And here you see the predictions, the depth predictions are indeed quite convincing in the middle column, but also note on the right side, for example, in the areas of the window, we get very high estimates of this uncertainty. So the uncertainty prediction is also fairly convincing in this transfer to a new environment and a new dataset. Next, let's assess the performance on visual odometry. Here we compare first on Kitty, both with respect to classical optimization-based methods, but also with respect to deep learning-based methods. And as you can see, the proposed method D3VO significantly outperforms both monocular and stereo methods on this dataset. We saw that before. D3VO uses deep learning to enhance the performance, and that this allows us to get a monocular method to rival with state-of-the-art stereo methods. Turns out we can go even further. We can compare to so-called visual inertial approaches that use cameras and inertial sensor to track the location of the camera. Especially for rotational motions, typically the inertial sensor drastically improves the performance. So you can see that here when moving from monocular DSO to visual inertial DSO, we get a drastic boost in performance. We can further improve this to going to stereo inertial. For example, one of the state-of-the-art methods in stereo inertial odometry is a technique called Basalt, and achieves a very good performance here. The proposed deep learning-based monocular method shows the same performance as top stereo inertial methods, indicating once more that neural networks are sufficiently powerful to compensate for a lot of missing sensory information. Here are reconstructions, and on the left you see a monocular DSO reconstruction on a difficult sequence from the UROC dataset. As you can see, it's rather noisy. The reconstruction is noisy because the trajectory is inaccurate, whereas on the right, the deep learning enhanced method D3VO gives you significantly crisper reconstruction showing a significantly more accurate trajectory. Essentially, the key message in all this work is that direct methods leverage all intensity informations to get best performance in terms of precision and robustness. And the more we understand about how brightness variations in our world come about, the better precision we can get out. The key idea of deep learning enhancement is rather than us understanding the brightness variations, we train neural networks to understand these brightness variations and therefore further boost the performance of these direct approaches. Now in D3VO, we merely we did an affine transformation of brightness, and then for those areas that are not Lambertian, we basically down-weighted them with an uncertainty estimate, also with a deep network. But beyond down-weighting them, you can go further. For example, if you take really challenging sequences, such as these from the Oxford robot car dataset, we used images with very different lighting or weather conditions. For example, the top two images are the same sequence, but different lighting. You see very strong, pronounced shadows or reflections here in the water that give you very different brightness values. And on the bottom you see, for example, weather changes. The green grass all of a sudden is covered with snow. And so even for humans, it's not often easy to see immediately that we're actually looking at the same scene here, because brightnesses, colors, and everything changed significantly. And this is an issue for long-term tracking. If you come back to an environment and you want to relocalize in that environment, if the environment illumination and appearance change significantly, then just an affine correction will not do the trick. And so what we can do, and this is work by Lukas von Stumberg and collaborators called the Gauss-Newton net for multi-weather localization. The idea here is that rather than correcting these brightness changes with affine or other transformations, we basically create an entire feature representation with a deep network where we transform the brightnesses to a feature representation. This idea is not new. What is new is that we basically train the deep network to perform optimally in a subsequent Gauss-Newton based SLAM approach. And I don't want to go too much into detail, but the idea here is that we introduce a Gauss-Newton loss and we in some sense estimate or maximize the estimated probability of ground truth correspondence. And as you can see in the image on the right, we can estimate uncertainties that are indeed anisotropic and that allow for alignment in one direction more than in another direction. And so this indicates that the optimal correspondent is more likely in one spatial direction than in another. And this can then all be integrated into a SLAM approach, and then we can relocalize, for example, in a previously reconstructed world. Here the previous reconstruction is shown in white, and the current ongoing reconstruction is shown in blue. And as you can see in these videos, these two point clouds, the blue and white one, align very well. For example, on the lane markings you see it well. On the facades you can confirm it, showing that indeed we get very high precision. On the bottom you see the input. The current image is the second one here. The closest map image identified by the algorithm is the one before last, and then we come, and here you see, the challenging environment with moving objects, with bad visibility, and still we can track reliably and realign our world to a previously reconstructed world. Here on the right you see some parked cars in blue that were not there in the first time of mapping. And you see also the lane markings accurately aligned, the buildings aligned. And so this is a technique that we promote for relocalizing a car in a previously mapped environment. The benefit of doing so is in particular that we can leverage previous maps and previous information, and in order to align ourselves in world coordinates. So the idea here, you see, for example, a building construction site that wasn't there at the first time of mapping, and you see how the construction site aligns well with the building facade. And so we can update maps, we can ideally even identify changes in maps and all of that. Here's another sequence case where we show that we can map and align to a previous map, even in significant weather changes. The old video was run in summer and sunny weather, whereas the new one is in overcast and snowy environment, and still you see we get fairly nice alignments of the two sequences. How do we evaluate the performance of such a method? We propose the benchmark data set that we call the Multi-weather Localization benchmark, and it is made up of two sets of sequences. One set of sequences from Carla, from a simulation environment, where we have 9 sequences for training, validation, and testing. And these sequences are shown on the left, sometimes overcast, sometimes more sunny, so you get very different intensities and colors. The other remaining data sets are from the Oxford Robot Car, a real-world data set where we have 2 training sequences and 6 test sequences. And these sequences involve very diverse weather, and in particular one of the challenges we were able to resolve is we can train on a data set that involves sunny and overcast, and we can apply the same network without retraining to a setting where we have to transfer between sunny and rainy, or even between sunny and snowy. And this is an evaluation to competing methods, and it shows that the method works quite well. Here again, on the x-axis you have the relocalization error, and on the y-axis basically the number of successful relocalizations at that error. So I recommend that you try this dataset and evaluate your own methods for localization and relocalization across weather and lighting. To summarize, I talked about using deep neural networks for camera-based reconstruction. In the first part, I introduced methods to leverage the power of deep networks to do 4D animation at much higher resolution and precision, where essentially the network is trained to increase the resolution of normal maps using training data, and that generates temporally consistent high-resolution appearances of characters that look quite realistic and more realistic than previous approaches. In the second part, I introduced visual SLAM, in particular the concept of direct visual SLAM approaches that directly leverage the brightness values of the camera to get high-precision trajectories and maps. I then showed how you can use the power of deep networks to further boost the performance of direct methods, what we call deep direct visual SLAM. So the idea is that you have a deep network that predicts either just the depths or a number of other parameters, color transformations, uncertainties, etc. And then all of this is carefully integrated into a SLAM approach, both in the front-end tracking and in the back-end optimization. And you get a performance that rivals top stereo and even stereo inertial based methods while using only a single camera. I showed that you can also use deep networks to semantically label the world you reconstruct. So you can recover semantic reconstructions of the world. This is very important for self-driving cars and autonomous systems, that we not only reconstruct the geometry of the world, but we also reconstruct the semantic meaning of the world in order to distinguish what is the object that is in front of us. Is it a car? Is it a cyclist? Is it a pedestrian? Or is it a building or a tree? This allows us to achieve, to my knowledge, unprecedented precision in localization, in particular in GPS-denied environments, say tunnels or parking garages. And we also develop deep learning-based techniques that allow you to relocalize in a previously mapped environment using what we call the Gauss-Newton network. That's all. I thank you for your attention, and I'm looking forward to a lively discussion.
So I would like to thank Daniel Cremers, who has joined us live right now. Can you hear us, Daniel? And let me also remind everyone who has joined us that it's actually possible to also watch us on YouTube in your favorite browser, and also ask questions that get posted here as well to our speakers and keynote speakers as well. Daniel, are you with us?
Hello, can you hear me?
Hello. Yes.
Yes. I had some trouble with my headphones just now. I hope it's working. I hope you can hear me. I hope there's not too much resonance. But this is the problem with Bluetooth headphones. When you need them, they don't work. Okay. Should I just go and answer the questions that you marked?
I think the best way to do is that I probably need to read them aloud for our YouTube audience also to hear it. So one question came from the YouTube, actually. It was a question by Jiaming Sun. So is it possible to integrate deep features into Gauss-Newton net into the online optimization in direct SLAM, such as minimizing feature metric error instead of photometric error?
Okay, first of all, that's a very good question. And I should say, to some extent, that is more or less what we do in the Gauss-Newton net approach, is that these features are then used in a SLAM approach, very much like direct sparse odometry. So rather than aligning intensities, like in the classical intensity-based direct SLAM approaches, we use these features that the network generates. So we transform both images or all images into that feature space, and then impose consistency of these features. And these features are designed to be, they are trained to be maximally invariant across lighting and weather.
If you allow, I also have a follow-up question. So you often in your lectures and in your talks, you give a very broad, a very profound historical perspective on the vision-based methods for reconstruction. And one question is, it seems that a lot has been actually done in vision-based sparse reconstruction during the last decades. And do we actually need novel methods for reconstruction? So maybe we can leverage what has been created previously and integrate all these various data modalities such as semantics and depth and other signals into the nets, or do we need something completely new? Should we expect a revolution coming from deep nets in the vision-based stereo?
That's also a good question. I do believe that in research, there's always a value in questioning the classical approaches and tackling new ideas and basically looking at a problem to some extent from scratch and seeing is the traditional way really the best solution to this problem, or is there not possibly a better solution? And I think what drives all of us researchers is that vision that everything can be done better, that everything can be challenged and improved over. And I think this is also true for camera-based reconstruction, where, for example, rather than pursuing the classical keypoint based strategy, we promote these direct methods and have shown, I think, convincingly that this does lead to a drastic improvement. And I think in a similar fashion, we will see in the coming years drastic improvements coming through learning-based approaches. But I think what it takes to make this happen is to understand how we can merge the benefits of let's say the predictive power of neural networks with the strengths of classical methods. And the challenge here is, in some sense, to see that the classical methods, they use knowledge about how the camera works, how the world is projected perspectively into images, even how brightnesses can vary with the light hitting a surface, etc. So there's so much knowledge about these physical phenomena. And one of the key questions that we need to address in this respect, but I think in general in the deep learning community, is how we can bring that expertise and knowledge about the world back into the learning-based approaches, that we don't learn things from scratch that we already know. And so this knowledge about the world needs to be integrated and coupled with the learning-based approaches. And this is the challenge that needs to be resolved to make things work better.
Thank you. So deep thoughts, don't just swallow the data.
Yeah.
Yeah. Okay. The next question from Zoom is that have you also used simulation for extreme lighting changes or even unusual colors like light green or dark red? I'm not 100% sure what this question relates to, probably the SLAM method you were presenting.
So yes, so I don't know when people pose the question. I think some of these questions may have been posed in the middle of the talk. Indeed, yes. To some extent, the last part of my talk, the Gauss-Newton net, addresses exactly that, where we tackle rather, it's always a question what you call extreme, but if you have, I showed some examples in the talk. If you have images that show, the world in regular daylight and sunlight, and then the same world in snowy or rainy conditions, that are significant changes. In fact, these are more or less the changes that we typically have to face when driving through the world across the seasons and across weathers. And this multi-weather data set tackles exactly that. And so the networks are trained to deal with these kinds of nuisances and variations. My guess is similar approaches could be trained with possibly more extreme cases if you want. But I think the strategy is nevertheless the same one.
And the next question is, how effective is D3VO in doing indoor reconstruction using handheld cameras or cell phones that additionally suffer from rolling shutter distortion? And what method would you recommend to handle this case specifically?
So this is a very difficult case indeed. I mentioned direct methods are very powerful. And they do perform better than traditional methods, but this holds for global shutter, and where the assumption is that all images, each image is taken at one specific time. Once you have rolling shutter cameras that are quite frequent in cell phones and in cars as well, then the assumption that the entire image is taken at the same time is not quite accurate. If you look into SLAM approaches, most approaches still make the assumption, even though they know that it's not valid. This leads to a distortion. So the point is not exactly where it should be. These distortions we find are rather not good for direct methods. And we find that the more traditional geometric bundle adjustment approaches, they tend to work better with distortions that come through rolling shutter. The reason is that they minimize a geometric error, so they're actually designed to be robust to distortions, to spatial distortions, whereas photometric errors like the direct methods are designed to be robust to photometric variations. And so the cost functions are different, and hence the robustness to different perturbations is different. For example, direct methods are extremely robust to downsampling images, whereas keypoint-based methods suffer. But in turn, we found rolling shutter is a serious issue. There is, I think, many ways to deal with it. One is to ignore it and hope that the effect is not strong. One way is, if you know the rolling shutter effect, you can pre-calibrate it and compute it. If you need to estimate the rolling shutter effect along with the reconstruction, we have done that. This is a work, I think maybe last year or so, for 2018 ECCV, we had a talk, direct rolling shutter, direct sparse odometry, where we explicitly model this phenomenon. That gives very nice results, but at the sacrifice of having additional computational overhead. So at that point, it wasn't fully real time anymore. And so to some extent, it's, for me, I find still an open challenge how to devise a direct method that can deal optimally with rolling shutter, but is still, you know, very efficient and real-time capable.
And maybe as a follow-up, I would like to ask one question from myself. So related to the mobile reconstruction, indoor reconstruction from mobile devices. So many companies are now releasing depth cameras as part of the cell phone, actually. And people are starting to look into these sensors for 3D reconstruction. Do you believe that in the next years, these time of flight sensors will be sort of challenging the old approaches to visual reconstruction, or maybe to visual SLAM in any way?
There's a number of new sensors coming out over the last years. One is what you mentioned, time of flight sensors, you know, RGBD cameras in general, like Kinect, Asus, PrimeSense, RealSense, whatever. There's quite a number of them out there now. There's other cameras that are coming. For example, event-based sensors are quite interesting also as a novel sensory technology. I think they will not necessarily replace classical cameras, but the way I see it, they will complement them. And in my experience, all these different sensors have their strengths and their shortcomings. So time of flight or RGBD cameras in general, the strengths is that they essentially give you the depths. And so you don't have to reason about correspondence estimation and all of these the challenges of finding correspondence, identifying the depths indirectly through color consistency. But you can just read it out. I mean, this is a major benefit of RGBD cameras, but at the same time, they typically have limitations. For example, they have limitations in range, limitations in outdoor capability. They typically don't go beyond 7 meters range, not even, often more like 5 meters maximum distance. For self-driving cars, for example, this is not a good option. If you have a maximum range of 5 meters, then good luck with a self-driving car. So you need longer range. You need to be able to cope with sunlight as well. This is another big limitation of RGBD cameras. And another limitation is that they tend to be quite power hungry. For example, in RGBD sensors, if you want to increase the range, then that's a sacrifice of paying a lot more power consumption. And whereas regular passive cameras are very low power and very small, very lightweight. So classic cameras still have a lot of advantages here. Similarly, for event-based sensors, I think there's many benefits. They, in principle, offer a higher frame rate. There is no really the notion of a frame, but you can look at how many events you can stream, and then you can talk about something like 10,000 hertz, which allows you faster reaction to certain things. Also, sometimes they seem to be better in low light conditions and so this can bring in a benefit, but at the same time, my experience is that the signal to noise ratio in these event-based cameras is not really convincing yet. So maybe there needs to be still improvements there. Also, at this point, to my knowledge, event-based sensors are to date not really available at very low cost. I think companies are working on that, but there's a little bit of chicken and egg problem here. We need to first show that these cameras can be used for something with algorithms, and then once they go into mass production, they will also become more affordable. But I think a lot of these sensors will not replace the traditional camera, but complement it in many ways.
Thank you. So I believe, well, maybe we can take another last question, or are we low on time? Bernard, what do you say?
I think we should take one more question, but then also go to the papers that they definitely have enough time before the next keynote.
Yes, thank you. So let me probably ask the question from Alexei. So is it, well, the question is, how is it possible to leverage temporal information to smoothen the behavior of the predictions of the neural networks at any particular moment in time? So we have seen these flickering effects and oscillations in many methods that try to deal with videos but don't take any temporal information into account. So what is your view on that? What's probably the best, paradigm for self-driving cars, or any other specific area in your experience?
So I think it depends on what you want to do, but this is a common problem if you apply deep networks just on a single image independently from image to image, then obviously that's what you can expect, that the output is not temporally consistent. But so essentially there's many ways to tackle, but I think it's fairly straightforward to bring in temporal regularity into deep nets for image processing. For example, you can take two consecutive images and always assure, or you can take the output of on the old image and add that as input with a new image, and make sure that the output of the network not only processes the current image, but is also consistent with the output of the previous net. I mean, this can easily be integrated, this kind of temporal continuity. And we've done this, and we found that that works very well, and it allows to remove the flicker. In fact, what we showed is that this is very important for making this work on SLAM. Because if you process one image into a feature space and then the second image independently, and then you want to argue that the features should be consistent, then you get issues, because the consistency drives the whole SLAM. And so you need to assure in the deep net that you get temporal consistency of the output. Yeah.
Okay, thank you. I would say that that would be all for this Q&A session with Daniel. Thank you so much for joining us live, for taking this time.
Thank you very much, Alexei. Thank you, Bernard. It's been a pleasure.
It's been a pleasure for us.
Thank you very much.
Thank you.